Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 16th episode in a series that seeks to demystify programming in assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you'll know when the next episodes come out, and start this playlist from the beginning. So far in this series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works, and since then, getting into the specific capabilities of the X16. We've seen already how to do some timing with the Vera display adapter, which triggers an interrupt that coincides with the video output vertical sync signal, otherwise known as the VSync IRQ. We've also seen how simply executing instructions takes up processor cycles, but there are a few other ways to handle timing with the X16 that are more appropriate for certain applications. But first, let's review what we know about timing already. The VSync IRQ happens at the beginning of each video frame, 60 times a second. That means 16 2/3 milliseconds go by between each one, so we can use that to time things that only need that level of granularity. This does require to use a custom IRQ handler to count the VSyncs, and then fairly heavyweight math for the 65C02 to convert these tick counts into seconds, and at best estimation for conversion to milliseconds. And it requires you to define your own storage and code to make VSyncs work like a real-time clock. Meanwhile, the smallest granularity we have is with instructions that can burn clock cycles. Mostly, this is with no-op instructions, which spend 2 CPU cycles to do nothing but advance the program counter, which works out to 250 nanoseconds per no-op for our 8 MHz system. That's great if you have to do some low-level hardware interface, and you can just do 4 no-ops to make a microsecond pass by. But if you need a millisecond, though, then it's 4,000 no-ops, and that's not an efficient use of code. You'll have to do a loop and calculate the timing for all the non-no-op instructions as well, and there could be differences in timing for some opcodes when they have to access memory across page boundaries. On top of all that complexity, the timing is completely invalid unless you have interrupts disabled, and in the interim, nothing of value can be accomplished other than the waiting. The CPU is also running at full speed, using unnecessary power during a busy loop. There are better ways to do this, and we're going to see some right now. One option we have in between the VSync cycles and individual no-ops are Vera line interrupts. In addition to having an IRQ at the beginning of each frame, we can configure Vera to generate another IRQ for somewhere in the middle of the frame, right before it puts out a specific line on the display. Regardless of display scaling, the Vera is always putting out 480 lines of video, and it can generate a line IRQ for any one of those. In fact, you can have one line IRQ trigger a handler that will set up the next line IRQ to happen later in the same frame. With VGA output, the Vera is putting out all 480 lines between each VSync, so you can get your interrupt granularity down to a single raster line, which takes about 31.78 microseconds. If you are using an interlaced NSTC display over a composite or S-video, you can only set interrupts for even line numbers, which brings your minimum line IRQ cycle to about 63.49 microseconds. In either case, you can only trigger interrupts for lines that are visible. Vera does not support line interrupts during the vertical blanking period. We've seen the Vera interrupt control registers before, but here's the same slide again for review. For line IRQs, we need to set the line bit in the IEN register, and then the line number in the IRQ line register. As the range is 0 to 479, we need a 9-bit value, so the main line register is only the lower byte, bits 7 through 0 of the value. Bit 8 is specified back on the IEN register on the highest bit there. Then, during the IRQ handler, you can see if the current IRQ is for a line interrupt if the line bit is set in the ISR register. Then, after handling the IRQ, you can write those set bits back to the ISR register to acknowledge that they've been processed. This will ironically clear the bits when the next IRQ comes around that wasn't triggered by the same thing. The ISR bits act as latches otherwise, staying set until you write ones back to them. In earlier episodes, we talked about Vera layer configuration, and how each of the two video layers has to have its own configuration. This implies that each layer can only have one configuration, and that's not actually true. You can use the line IRQ to change a layer configuration for a set of lines, and in this case study, we are going to split layer 1 in half, with the upper half using the default 16-color text mode, and the lower half displaying 256 color text by setting the T256 bit halfway through rendering the display, then clearing it again when the next frame starts. First, we need to define some addresses, including the IRQ RAM vector, some Vera registers, and then a global word to store the original address in the IRQ RAM vector before we overwrite it with the address of a custom IRQ handler. Then we start the setup IRQ subroutine in the red code by copying the default IRQ handler address to the word we labeled default IRQ. We continue into the blue code, where we disable interrupts while we overwrite the IRQ RAM vector with the address of custom IRQ. But then, instead of just setting the vsync bit like we usually do at this point, we have green code where we set both line and vsync bits in the IEN register. Then we set the IRQ line number to 240, which will make an IRQ happen exactly halfway through rendering the 480 visible display lines. Then we revert back to blue code where we re-enable interrupts and return, just as we would normally. Then we define custom IRQ with the next bit of red code, and when an IRQ first happens, we want to check the Vera ISR register to see which kind of interrupt this is. If the vsync bit is clear, we branch ahead to @check_line. Otherwise, this is a vsync interrupt, so we set the layer 1 config to hex 60, which will give us the default 16-color mode that it had been at startup. Then we unconditionally branch ahead to @continue to finish the handler. If this wasn't a vsync, we would have branched to @check_line and executed the green code. First, we check the line bit in ISR, which should be still loaded in A, and if that's clear as well, then this wasn't a Vera IRQ. So we just branch ahead to @continue. If line was set, then we set the layer 1 config to hex 68, which will set that T256 bit, making the lower half of the screen use 256 color text mode. At this point, we fall to @continue, which will happen for all IRQs, and we make sure to reset all Vera IRQ latches by writing 3 to the ISR register, which will clear either latched bits for vsync or line IRQs for the next interrupt. Then we can jump right into the default IRQ handler and let it return from the interrupt after doing its processing. You could then have other code to populate the text map, and just make sure to use the right format of color specifications for each half of the screen. Now, if you want to go big, the X16 also has a built-in real-time clock, or RTC, which can be set by the user once and will automatically keep ticking away every vsync cycle. It keeps track of the year, month, day, hour, minute, second, and even the jiffy, which counts the vsync since the last second tick. So it gives you the same granularity as counting your own vsyncs, but it automatically takes care of all the date and time math in the kernel. So whenever you need the date and time, you can get all the fields in a quick subroutine call and populate the fields on the 0 page. Both the get and set subroutines for the RTC use the so-called 16-bit ABI, or Application Binary Interface. This is a 32-byte segment of the 0 page that is used by certain subroutines that were created for the X16 kernel. While the value these particular subroutines use are 8-bit, there are 7 of them, so this semi-reserved area works as well as anything. Sadly, because even the year is stored as an 8-bit number, the X16 RTC will cease to be functional after the year 2155, so make sure your upgrade path is planned ahead of time. Let's take a closer look at that ABI. It provides 16 virtual 16-bit registers on the 0 page, which makes them both quick to work with and capable of use with special addressing modes. Of course, some subroutines may reference single bytes within the ABI, but the way they are used is consistent. The first 6 registers can be used for arguments or return values, the next 5 for return values only, and the last 5 for scratch memory during the execution of some subroutines. You don't completely lose general access to these addresses, and they will only be modified by certain kernel subroutines, but if you don't use them, you can use these addresses however you want, or as scratch memory in between calls to the kernel. Just be aware that if you do use this part of the 0 page for other things, If you call the kernel subroutine that uses the ABI, it could potentially overwrite any data you have stored there. The clock set date time subroutine at hex FF4D only needs to be called once after the X16 starts up, and the RTC will continue to update in the background every vsync. It will take the year from the value in the low byte of R0, which is the address 2 on the 0 page. The RTC uses an epoch starting with the year 1900, so if you are feeling really retro, you could put in a value under 100 and be back in the 20th century. If you wanted to actually be in the pedestrian year of 2021, you can put in 121. This is why you'll need to upgrade your X16 before the year 2156, as the clock will roll back to 1900. The remaining fields are simply the values you'd expect, with 1 based months and days, and an hour that goes from 0 to 23, as there is no flag for AM and PM. The Jiffy field goes from 0 to 59, just like minutes and seconds, and that is the last field used, which is the low byte of R3 or address 8 on the 0 page. No other bytes in the ABI segment are affected. Once the clock is set, you can call the clock@date_time at hex FF50 whenever you need the updated value of one of those fields. They will be loaded into the same ABI bytes where the original values were stored for the call to clock_set_date_time. The values are formatted the same as well, and you will need to add 1900 to the year value if you plan on printing it out as 4 digits, or subtracting 100 if printing 2 digits of a 21st century year. Rather than see a case study for the RTC, let's jump right to our example program. We had made a stopwatch before, but now we're going to make that a proper clock using the RTC interface. And rather than minutes, seconds, and jiffies, we'll display the hours, minutes, and seconds like a normal clock. We'll use Petsky text again, but blow it up to 8x scaling, and use line interrupts to change the colors of the characters as they're being rendered, creating a sort of shading effect. So let's see the code. After our segment preamble and jumpstart, we start our constants with the ABI registers. We only need R1H and the 2 bytes of R2 to get the values we need, but we might as well have all the registers up to that point defined. As you can see, we only use hard-coded addresses for the 16-bit registers, and then base the low and high byte addresses on those constants. Then we have the IRQ RAM vector, which we'll need to overwrite. Then we have all the Vera registers we need to use, as well as some values to use with them. New to this section are constants that we'll use for the line interrupts, and a display scale of 16, which will get us the 8x zoom we're looking for. Then we have the 3 kernel addresses we need, including the one we just learned for clock@date_time. We need to define some Petsky codes, including the code for Q, which we'll use to quit the program. To place our text, we have a couple of constants for the column and row indexes we'll use to calculate our VRAM addresses and line numbers. For global data, we need the backed up default IRQ handler address, variables to hold the decimal versions of our time fields, a counter to keep track of our line interrupts, and then the colors we are going to set during each of the line interrupts to get the shading effect we want. In all cases, we'll have a blue background with 6 in the upper nibbles, then white and the 3 shades of gray in the lower nibbles. Finally, we have some calculated constants for the number of raster lines per pixel, which should come out to be our zoom level of 8, and the lines where we want to start and stop changing the colors. Here we are taking advantage of our zoom level to have our color changes happen in the middle of the zoomed pixels by starting half a pixel height above the tops of the characters. This will make the darkest gray only apply to half-pixel rows across the tops and bottoms of our numbers. The Petsky number glyphs are only 7 pixels high, so we can cover the full color swath over 8 lines. Before start, we reuse the print decimal macro from the stopwatch program in Lesson 10, which will write the correct screen codes for each numeral of a decimal byte. At start, we clear then scale the display. Then we call the print display subroutine. This is based on the subroutine of the same name from the stopwatch program, and we'll see how we change that later. Then we initialize our line counter before we set up our interrupt handling. Of course, we need to back up the default IRQ handler to the address we allocated. Then we overwrite the vector with the address of our custom IRQ handler, enable line and vsync IRQs, and set the first line interrupt to happen at the start line value we calculated earlier. We know that start line is under 256, so we don't need to worry about setting the high bit in the IEN register. But that will change as we adjust the IRQ line later. With the initial interrupt states all set, we can re-enable interrupts and continue on to our main program loop. Our main loop will simply wait for interrupts, then check the keyboard buffer to see if Q has been pressed yet. Once it has, we fall out of the loop and restore the default IRQ handler, and enable only VSync interrupts, leaving out the line bit. Then we reset the display scale so that we don't have enormous characters anymore, and clear the screen before we return to a manageable basic prompt. The custom IRQ handler will first check the ISR register to see if this was a VSync IRQ. If it wasn't, we'll branch ahead to @checkLine. Otherwise, we handle the VSync by calling printDisplay to update the time shown on the screen, then resetting the line counter to 0 and branching ahead to @continue to go straight to the default IRQ handler. If this wasn't a VSync, we check the ISR value still in A to see if the line bit is set. If that's clear as well, we branch ahead to @continue, knowing that this wasn't a Vera IRQ at all. Otherwise, we are at the beginning of the IRQ line, so we set up data port 0 to start with the color spec of the first display character, whose address we can calculate using the display constants, with the low byte set to the X value times 2, which would give us the screen code, then +1 to get the color spec. We get the color spec value for this line by loading the current value of the counter into X, and using that as an index into the color wave array to load the spec into A. Then we load 8 into Y to loop through all 8 characters in the display. The loop is very simple, as we simply store that color spec into data port 0, which will advance to the next color spec as our stride was set to 2. Then we decrement Y until it gets down to 0 and we fall out of the loop. Then we can increment counter for the next line, and add the number of lines we have in each zoomed in pixel to the IRQ line number. If the carry bit is still clear, we can branch ahead to @setLine. Otherwise, we need to set bit 8 of the IRQ line number, as we have crossed past line 255, and we need that bit set for the rest of the frame to get to those later lines. Either way, we fall to @setLine, where we compare the line number to the low byte of the calculated stop line. If those don't match yet, we can branch ahead to @QuickReturn. Otherwise, we made it to the last line interrupt of this frame, so we can reset the IRQ line back to start line. Falling to @QuickReturn means we have finished processing a line interrupt, and we want to get right out of this IRQ handler as the next one should be happening pretty quickly, and we don't need to call the default IRQ handler again after just calling it during the last VSync. Going through the full default IRQ handler will actually take a few lines, depending on what happens, so this is the best practice for line IRQs. But just before we return, we need to make sure we clear out our Vera IRQ latches by writing the line and VSync bits back to the ISR register. Then we have to pull the registers back in the opposite order they were pushed by the kernel before it called our custom IRQ handler. Then we just do an RTI and we can get back to the main loop and wait for the next IRQ. If this was a VSync or any other kind of IRQ, we could have fallen to @continue, where we also want to clear those Vera IRQ latches, then go ahead and call the default IRQ handler, as we should have time to do that now. In our new print display subroutine, we start by calling clockGetDateTime to populate the ABI registers with the current time. Then we need to convert each field from binary to decimal, starting with the hours, which we load into A from R1H and call bin2dec. This subroutine will take a binary value in A and convert it to binary coded decimal and put the result right back into A. Since we know the clock will only be dealing with 2-digit values, the 8-bit accumulator will be able to hold the entire decimal number. We'll see how this works soon. Meanwhile, we store the results in the hours variable and continue to convert the other two fields, getting minutes from R2L and seconds from R2H. Then the rest is pretty much what we had for the stopwatch, setting up a stride of 2 to set the new screen codes, and calling the print decimal macro with each converted field. Then we return back to the IRQ handler to finish VSync processing. The bin to deck subroutine is the simplest possible binary to decimal conversion you can do. We start by branching over local variables that we'll use for storing the initial binary value and the decimal result. We then store A into @bin and initialize @bcd to 0. We get ready for our loop by loading 8 into X and entering decimal mode. Each iteration, we shift the high bit of @bin into the carry bit and add that in while we add @bcd to itself. We decrement X and keep going until each power of 2 is added in and X gets down to 0 and we fall out of the loop. Then we exit decimal mode and return. And that's it. Of course, we have a build script. And we're going to build this code into clock.prg, but you may be wondering where this time is going to be coming from. To take care of that, we have a basic program called setTime. This will prompt the user for each field in the real-time clock, starting with the year and going down to the minute. We set the seconds and jiffies to 0, then call clockSetDateTime. Starting with the emulator release R39, you'll be able to automatically set the RTC with your host system time, but this program will still be useful if you want to set a different time for testing. So let's get to the terminal so we can finally see our clock. All right, let's run build.sh and take a look at our directory listing. And we'll see we have a clock.prg, but first we need to load in settime.bas. Since this is basic source code, we can't load it from the basic prompt within the emulator. So let the emulator import the code as if it were typed to input by using the -base argument followed by the source file name. As you can see, the emulator comes up as if we just typed in the basic program at lightning speed, and now it's all in program memory. Let's maximize it for a better look. We have everything loaded already, so let's just run it. We'll put in the current date. That'll be 2021. April 19th is when this is premiering. And just for test, we'll set the time to 12:34. Yeah, just to match the screen cap we saw in the slides. And that's it. The RTC should be ticking away already. So let's load clock.prg and run it. And there we go. Our clock is now ticking, and we can see the seconds go up until the top of the minute. And there we go. Then it clicks to the next minute. And we can sit and watch this for hours, but you should get the picture by now. Blown up like this, we can really see the color shading we did and how the color changes split the pixels horizontally. So even though the display has blown up the pixels, the Vera line IRQs don't care about display scaling and can still provide timing for 480 raster lines. We can now quit by pressing Q, and we're back to basic. And that's all we have for this lesson. I hope this helped to shed some light on the different timing options available for the X16 and how they might apply to the programs you want to create. This timing can be used in conjunction with a lot of things we've done already in this series, and with some things to come. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button, and if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible, just like the folks you see here did on my Patreon page, which you will find linked in the description along with a GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye.